Hello, good evening, good afternoon from wherever you are. My name is Bob Afwata. I am the R&D engineer and co-founder of Focus Lens Electronics, which is a small R&D company based in Kenya. We do R&D on wireless communication, IoT, as well as product design. At my back, you can be able to see I have some 3D printers, which I have also in the past 1 year helped taught both academia and students on how to design around medical equipment or around healthcare. So I have skills in firmware development, embedded Linux, as well as PCB design. And also I've worked with the law enforcement agencies as a consultant in military and surveillance. So today I want to take you through a very interesting topic to me. This is part of my application for a master's program at the University of Daegu. Today I want to take you through the definition of terms. What is electromagnetic compatibility? What is shielding and shielding effectiveness? What are the various equations for electromagnetic shielding effectiveness, and also the derivation and also analysis. We will also look at it in brief, the applications in the industry. So electromagnetic shielding, electromagnetic compatibility, if I start from there, these are tests, or these are tests which are done in the industry to an equipment or to an electronic equipment before it is supplied out there in the market. There are a lot of factors that happens, and your device should be able to, before you take it to the market, before you put it in the hands of the consumers, be it for medical, be it consumer, be it avionics or military and defense, you should be able to ensure that your device cannot be able to cause stray radiation, or it cannot be able to interfere with other electronic devices out there. So these are the various tests that happens. Today we want to specifically look at what is called shielding, and a key important aspect called shielding effectiveness. Then we are going to derive some of the questions that are there and try to interpret them, as well as get the industry applications of these equations or of these concepts. So shielding, what is a shield? So a shield is something that protects. A shield is something that basically it's a metallic part which completely or partially encloses an electronic product or part of that product. So it's a barrier uh, to transmission of the electromagnetic fields. If you can see, these are, I'm holding here, this is a part of a tracker. If you can look carefully, so this is a PCB of a tracker, of a tracking device, which we have been using in some of our projects. You can be able to see there are those metallic parts, which are covering parts of the PCB where the antennas are. Just near there, you'll be able to see something which is also familiar with most engineers or most IT experts is what is called a Wi-Fi card. This is an Intel Wi-Fi card. It also has got some metallic part which protects the PCB or the electronics inside there. So that is what is called a shield. So why do we really need to have a shield? We need to prevent emissions from our product, electromagnetic emissions from our product, from interfering with neighboring electronics. So if you have your phone, you don't want it to transmit radiation, or you don't want it to transmit something that will interfere with the neighboring electronics, be it like a pacemaker. There was a recent news where Apple, which is the biggest brand making the iPhone, sent out a news brief about how their iPhones should not be placed near the heart. That is, should not be placed near the pacemaker or around your chest, on your side pocket, or on your breast pocket, because that will interfere with the pacemaker. So that's a real application of how this, when not done properly, can cause even death. Also, you want to protect your product from the emissions from your environment. You do not only want to protect other equipment or other users near you, but you also want to protect your device from stray electromagnetic emissions or radiation from the environment. We are going to look into this deeper, but the applications are in like mobile phones, radios, TV transmitters, radar for defense and aerospace, and all that. So there are some key components of the electronic product or key components of the product that you need to protect. So the new concept which we want to talk about is the effectiveness. How effective is that shield? Basically, when we talk about the effectiveness, it's a ratio. So it's the ratio of the electric or the magnetic field incident to the uh, electronic product to that which is passing through the barrier. So there are two electric or magnetic fields, one which is incident or one which is getting into the product, and then one which is leaving or the one which is passing through the barrier. So if you get the ratio of these two, the ratio of the magnitude, you take their magnitudes, then that is what gives you the effectiveness of the electromagnetic shield. Ideally also, when you look at it, it's also the ratio of the magnetic or the electric field through that electronic component or through that electronic product when the shield is in place. So that is the incident magnetic field, and when the shield is out or without the shield, that ratio also brings you that. It's also equivalent to the insertion loss. In transmission lines, we come across a concept called insertion loss, whereby it's the loss of power when you place a material or when you insert a material inside a transmission line or something like an optic fiber. And this is measured in decibels. So there is the idea of ideal effective shielding. Something ideal is something perfect, something imaginary, something which cannot be achieved in real world situation. It's a hypothetical value. So if you're having 100% decibel, that's a perfect number. What it means shortly or briefly, it means that the field has been reduced to a factor of around 100,000, which is great. But how are you going to achieve this? So it occurs when the shield is impenetrable. Like for example, we are having the shield here. When it is impenetrable, meaning that the electromagnetic field cannot pass, incident to that shield cannot pass through it. It also can happen when the electronics is completely enclosed. There are no penetrations, there are no holes, cables, seams, slots. It's an hypothetical or an imaginary situation. You have to note that any hole, as no matter how small it is, it will affect this effectiveness of this shield drastically. So cable penetration, for example, if you are having an electronic part, a shield, and then you are having a cable or a wire penetrating through that, it greatly affects that effectiveness of that conduct of that shield. So the applications you'll be able to see, for example, I have shown you that on cell phones, if you open the cell phones, you'll be able to see those metallic parts that are made of different metals. They are used as shield. There is the components, which can be the GSM modem, it can be the Bluetooth modem, it can be GPS, it can be other signal processors, DSP, image signal processing, all those that make up the phone electronics. You need to protect it. Also, this also has been used in lab equipment or like in physics labs, in research institutions. The second picture just shows you an example whereby you need to protect your signal from, if it is a signal generator, if it is a signal analyzer, before you analyze it, before you manipulate it, you need to have some protection so that you get good signal quality for analyzing and for doing your operations. Also in avionics, something like a missile guided system or a rocket, when it's headed like the SpaceX rocket that is headed to Mars, out there in space, there are a lot of electromagnetic radiation that are found in the ionosphere or the upper part of the atmosphere. So you need to protect your electronics. You need to protect them so that the radiation does not fry your electronics, your delicate electronics found inside there. So these are some of the few applications of shielding. So here now we want to look at what is the mathematical derivation, or what do we mean by the shielding effectiveness. The shielding effectiveness, SE, is got by the logarithm, 20 logarithm to base 10 of EI. EI for this case is the incident electric field, which is a vector, and ET is the transmitted, or the transmitted electric field, which is also a vector. So it can also be taken in terms of the magnetic field. EI is for electric, HI is for magnetic fields. So then you get the ratio of the incident magnetic field, HI, and also the ratio of the transmitted, HT, you will also get that. So it's a vector, meaning it has got direction and magnitude. So the ideal way to represent it is put EI with an indication of the direction, or where in the X, Y, Z coordinates where it is. We are going to see that. So HI, as we have said, is the magnitude of the incident magnetic field, while HT is the magnitude of the magnetic field as it exits or through that barrier. And for this value of SE, or shield effectiveness, to be positive, from there, simple math, you will have to have EI being greater than ET, or HI being greater than HT. The incident magnetic and electric fields have to be greater than the magnetic fields, the magnitude of the magnetic fields as it exits or as it leaves the barrier. So there are sources of these electromagnetic sources, or electromagnetic losses. There are reflection losses, absorption losses, and also multiple reflection losses. These are denoted by RE for in this formula, AB for the absorption, and MR is for multiple reflection. So where do these losses come from? When the signal gets through a waveguide, or when it gets through two sets of parallel material, then it is reflected, and it gets reflected, and some of the material gets absorbed by the two parallel material. You can be able to see there is the reflection, which happens as the signal bounces from top to left, and that is what causes the reflection losses. Absorption is caused when the signal moves through a surface, through a medium, for example, through air. Then there are particles, air particles, clouds, vegetation, water droplets. These signals, when they hit the particles, the dust particles, the water particles, they transfer that energy, because it's basically energy. They transfer it and make this, the particles vibrate or move. It transfers that energy, and that causes the loss. Then multiple reflection, remember, as it's going through these various medium, there is a lot of reflection from various mediums or from various components in that. That is what causes the multiple reflection. So the exact solution, we want to look at what is the exact solution of the electromagnetic effectiveness. This is where you need to buckle up. There's a lot of mathematics coming up, but I hope you'll be able to understand it. So before we start, I want you to take a scenario whereby a conductor, which is which is aligned in the X, Y axis. The conductor has a thickness of T in meters, conductivity of tau, epsilon, which is the permittivity of the conductor. And remember, there is epsilon and epsilon naught. Epsilon naught is actually the permittivity in free space, or when there is no air in free space. Then mu is the permeability of that material. There is mu in any space or in any material, but mu naught is in free space. So we want to assume this signal is incident to a surface. So from Maxwell's equations, we can be able to get that the incident radiation EI has got EI raised to power E epsilon j beta and then beta naught, and it has got basically what this equation shows you. I'm going to show you a better derivation. It's basically telling you that the incident electric field has got an x, it's a vector, so it has an x component. And if the electric field also has got an x component. So when we look at all this, you can be able to derive them. So from this, I hope you'll be able to see from the first part, we looked at from the first part to your top left, you can be able to see SE is the logarithm, 20 logarithm of the ratio of EI, which is the incident electric field, over ET, which is the transmitted electric field. So similarly, you can also take it in form of 20 logarithm of HI, which is the magnetic field, and HT, which is the transmitted magnetic field. And the sum, which is R plus A plus M, all of this is in decibels, is what constitutes SE. So those are the two formulas that you need to know when you are deriving this. So this is our diagram. This is a plane which is aligned along the y-x axis. It's a normal plane with a thickness T, a permittivity, conductivity, and the conductivity is how current is transmitted through the current, how much current per unit voltage is being transmitted through that. So from Maxwell's equations, we can be able to see that the incident electric field, EI, has got an X component. It also has got a Y component and a Z component. That is the key thing. So you can be able to resolve the vectors, or you can be able to split them into three. Similarly, HI, which is the incident magnetic field, also has got the X component, Y component, and the Z component. So what I have shown here is just the X component and the Y components. So that gives us equation 1 and 2. Then HR from basics electromagnetostatics, it is ER over N tau, which if you solve, you're going to find that replacing from above there, you'll be able to see that ER, which is the radiated, you see we are getting a radiation. We are getting the first component, which is the because of the reflected, because of the reflection, we are getting the first component RA. The RA is gotten, the ER as a result of radiation, reflection, is equal to ER, which is the incident, but it has got a Y component. Similarly, ET is ET, and remember it is a vector, so it has got the direction. You can see over there, you get the Z component, or it's on the Z axis. So you can be able to see it from the diagram above. So when we compare in free space, I told you there is beta naught, which is actually gotten by the angular frequency omega, and then the square root of epsilon naught and mu naught, which is in free space. Those are the permittivity and the permeability of the material. Then the propagation constant is gotten by the formula propagation constant beta. The propagation constant, not beta, but alpha is J. It's a complex. It's a complex variable which has got both the real part and the imaginary part. So the real part is alpha. When you resolve this equation, is alpha plus J beta, where beta there, and then the angle there, the angle which you got there is also what is called the intrinsic impedance. So what is the impedance of this component? Remember, impedance is like having a both resistive, it's behaving like a resistive component and a magnetic component, or with some elements of an inductor. So it's behaving like an RL circuit. So those are the two components that we're having there. So when we consider, there is an interesting part which is called boundary conditions. So as you can see, the equation is going to get a bit complicated, but we need to simplify the equation by introducing boundary conditions. So boundary conditions is used to get the remaining amplitude. For example, if you look, if we take that from the diagram, if Z, which is the direction in the Z-axis, is equal to 0 and Z is equal to T. So when we put that, I will not explain for the all, but I'll just give you for the one component, which is the incident electric field. It's having a direction. When you give it Z is equal to 0 plus E R, Z is equal to Z is equal to 0 and Z is equal to 0, then it's equal to E1, which is on the first component, plus E2, and you can be able to see when we place the boundary conditions. So it will be resolved into E1 T, where Z is equal to T, plus E2, when Z is equal to T, is equal to the ER when Z is equal to T. So that is how it's resolved. Similarly, you can resolve it for the magnetic component. And remember, all this, we are going to place it, we are going to replace it into the original formula. So EI will be ER plus E1 plus E2. And all these are where EI is the incident, magnetic electric field. ER is the reflected, and then E1 and E2 are the components which get reflected or which get transmitted. So when we replace there, we'll get that E1 over N is equal to E raised to power R tau minus E raised to power R e tau over N. So this is actually the question how it comes. And it becomes, so this is the ratio. So you look at the ratio of EI. Remember we said that SE, in brief, it's the ratio of EI over ET. So this, when you replace the formula, it becomes this complicated. And for us to solve this, or for us to resolve this, we need to get the logarithm. The idea of logarithm will come in. But if you look here from this equation, we can see that this is the exact expression of the ratio of the electric field that is incident to that of the electric field that is transmitted through the conductor. So this long formula is the effective or the exact expression, or is the exact is the equation for the exact shielding effectiveness. We can resolve it further by getting what is called delta, which is 1 over the square root of pi f, f, which is the frequency, and the mu delta. So this is actually which is called the standing the depth, the skin depth, sorry, the skin depth of the barrier. So that is the skin depth of the barrier, and you can be able to resolve it further. So when you get that N is much, much less than N naught, we can be able to replace the middle part with 1. So we just, because we are doing an approximation in physics or in electronics, in science, you can do approximation, whereby the difference over the sum, if that value is much, much smaller, if N is much, much smaller than N naught, then you can assume to have the ratio of their differences to the ratio of their sum to be equal to 1. So that will give you that the middle component will be replaced by e raised to power ryt is equal to e raised to power minus j omega e raised to power j et. So that is how the formula will finally be simplified. And then the last page, or the last page, that same ratio, if you look at it, it can further be simplified by getting the logarithm. The logarithm, 20 logarithm, and then you can be able to get of n naught over 4n. This we have resolved above, and plus 20 logarithm e t over r plus md, where m is the multiple reflection losses, and md can also be finally be gotten as 20 log to power 10 1 minus n naught minus n plus n squared e raised to power 2t r raised to power that. So that finally the equations comes to 20 logarithm of the magnitude there, 1 e raised to power et minus tau over tau e raised to power j 2t over tau. So basically, that is the question. It's a long one, but the key things to understand, I just want to simplify this for somebody who is maybe rusty in vectors. You have to know that the magnetic field and the electric field from basic EMF or electromagnetic theory, we know that they are at 90 degrees, or they are perpendicular to each of them from the first diagram. So the incident electric field is EI, and then the transmitted, or the electric field through that medium or through the barrier is ET. So when you get that ratio, you can represent it in form of the electric field or the magnetic field. And then you need to resolve both the x, y, and z components. It's a vector, meaning that it has got both the x, y, and z components. You can be able to resolve them. Then after resolving them, there are key factors to look out for. Like for example, beta naught. Beta naught is the free space. So in free space, it's beta naught is equal to omega, then the square root of mu naught epsilon naught, which is the permittivity, the product of the permittivity and the permeability of that device, or of that shield. Then you can further, and then n naught, the Greek letter neuter, is the square root of the ratio of mu naught over epsilon naught, which is and then you can be able to get the propagation constant. And this propagation constant is a complex variable. It has got both the real parts and the imaginary parts. The real parts in this case is alpha, then the imaginary parts is j omega, and then the intrinsic impedance in this case is that phase difference, or the phase angle, n tau n. Then to get to resolve your question, because it will become very complicated, you need to introduce boundary conditions, and these boundary conditions are placed when z is equal to 0 and z is equal to t. These are arbitrary values which help us to solve the question in a similar way. So you take the incident and the reflected, then you compare it to the two components. This is hi when z is equal to 0, and hr when z is equal to 0. So those are the boundary conditions. Also, you can put ei when z is equal to 0 plus er when z is equal to 0. Remember, there will be no loss of energy. The energy incident will be equal or equivalent to the energy leaving the material. So when we replace it, then we get this complicated formula Basically, it's a ratio of EI over ET, and when you replace the complex math, you'll be able to get this long formula, which is referred to as the exact expression, or it's the exact, what we are looking at here, it's the exact solution of the electromagnetic shielding. So it's the exact, but it's an ideal situation, which does not happen. But remember, we are having three parts of this formula. We were having RA, R in dB, uh, which is the reflected component. Then there is the absorption, the reflected losses, then the reflection losses, the absorption losses, and the multiple reflection losses. So you can be able to derive them by replacing the values there, and getting to know something called skin depth, which is tau, which is an inverse of the square root of pi f mu tau. So it's a long formula, but you can be able to further simplify it by giving some conditions, like when t there is very much less than 1, or it's very much greater than delta. Then you will get the logarithm, the final formula when you are expressing it for easy application, or in calculations. You need to get the logarithm, 20 logarithm to base 10 of the whole formula. Then that will give you the SE in decibels. Remember, this ratio is expressed in decibels, of 20 log to power 10 of n naught over 4n plus 20 log to base 10 e raised to power t over tau plus md, which is basically the last component of the last part, which is the multiple losses. So that, in short, explains the formula. Then the applications we are looked in the military, in the biomedical, broadcast and TV, consumer electronics, scientific research, and all that. I want to be very grateful to the book which gave me inspiration, which is Electromagnetic Compatibility, which I've been using to study this, as well as other sources like the internet, which I've been using to study this great topic. So thank you very much, and I'm looking forward to hearing nice feedback from you about the topic. Thank you.